bizimkiler de. Arkadaşlar şöyle geç, oraya imza attırmayacağım. Bu tarafa geç. Okay, let's... Çalışıyor mu? Okay, last time we were talking about inter-process communication. We talked about semaphores. Semaphores were like, unlike the spin locks, they can block and later wake up when needed. Two operations with the semaphores, down and up. We talked about those. And we talked a special kind of semaphores. We said that there are two types of semaphores. One is a counting semaphore, okay, to count some kind of a resource, say, such as a buffer. And the other one is the mutual exclusion semaphore, which means make sure only one process is in the critical region. It's like a lock variable, but implemented using a semaphore. So it is something like that actually. This is a binary semaphore. The value is 1, when you make it down. If it reaches 0, then it blocks. Otherwise, it continues staying in the critical region. Okay. So two types of semaphores. And they say that if we are using these type of semaphores, then we use this mutual exclusion mutexes. O tarafta kal. We use these mutexes to use as a binary semaphore. Special case of, so mutex is a special case of semaphore. Okay. Useful when no counting is needed, so just to test the critical region stuff. That's what we use the mutexes for. And how it is implemented, we talked about this last time. Actually, I'm not going to talk about it. So it tries to grab a lock. If successful, then continues. Otherwise, other threads. O tarafta kalın. İmza atmayacaksınız siz. Otherwise, o tarafa kalsana. Geç şu tarafa kal. Yeni gelenler imza atmayacak, tamam mı? Derste zamanında gelin arkadaşlar. O tarafta kal diyorum sana, anlamıyor musun? İmza atmayacaksınız. Otherwise, other processes are left running. So this is mutual exclusion. Let's look at how the mutexes are implemented. It was talked about in the previous slide using test and set instruction. This is how it is implemented. This is mutex lock. And it is mutex unlock. And remember this one, TSL, test and set lock. What does it do? It does copy the value of this mutex to the register, okay, and set its value to be 1. And it is done atomically. And then we compare the register if it is 0, okay. If the register is 0, that means that nobody used the mutex before, so nobody locked it. So we go to OK and we return. Otherwise, we do what? This is what we do. Arkadaşlar bu tarafa oturun. Siz imza atmayacaksınız şu tarafa. Şu tarafa oturun. Bu tarafa oturun. Yoklama nerede? Neyi bekletiyorsunuz yoklamayı? Otherwise, okay, call thread yield. What does call thread yield do? Açık kalsın bari ya, sınıfın yarısı geç geliyor, açık kalsın. Gürültü olmasın. What does call yield, thread yield do?
Less other threads use CPU.
Okay, it blocks itself voluntarily and lets other threads continue, because if I am here, that means that I compare the register value with 0 and it is not 0. Then I come here, call thread yield. Okay, so when I reach this jump mutex lock statement, what happens? How do I reach here?
Try again.
What?
Tekrardan deneyecek yani.
Müteksler.
Müteksler.
Oh, okay. I thought you're asking me to ask again. Okay. So yeah, that's the reason. No. The question. I am not asking why we put it here. I am asking that under what situation should I reach this line?
If locked.
When do I reach this line?
Mutex is locked.
Mutex is locked.
So we keep continuing.
Şu tarafa otur, şu tarafa. Arkadaşlar bundan sonra şurayı boş bırakalım. Tamam, derse ilk gelenler buraya da olursunlar. Gençleri almıyorum değil de o tarafa tutsun gençleri. Oraya imza attırmayacağım bundan sonra. Tamam mı? Eğer yani orası dolacak kadar birileri varsa olur ama sınıfın bu kadarı var diye. So under what situation should I reach this line? I would reach this line after I call to thread yield. Okay. When it's time for me to start again, the operating system wakes me up, and I would continue from this one, and I would go back to the top, as your friend said, jump mutex lock, and test it again after the operating system lets me run again. Because after the operating system lets me run again, it doesn't mean that I got the lock. Okay, I have to test it again. So then I go there and test it again, and if the test is okay, I come to the return. And when I do the return, that means that I got the lock. Okay, so this is a non-blocking lock. It is not a spin lock. It doesn't waste CPU time, and unlocking is very easy. It just move 0 to mutex. That's it. Okay, it doesn't have to be done atomically. That's the only thing you need to do. Okay, any questions? So these are the mutexes. They are specialized versions of semaphores. They don't count anything. They are used for locking without wasting CPU time. Some people say that maybe I should. Okay, let's talk about this and we'll look at the example. Some people say that sometimes busy waiting or spin locks are more efficient. Why? Because if I don't block, okay, that means that if I get the lock, if I don't block, if I don't yield, then spin locks are faster than calling the operating system routines. Because when you call the operating system routine, okay, this one, when you call the operating system routine, that means that you're going to do a context switch. You are going to go into the kernel mode, and switching to kernel mode is expensive. Okay, it takes a lot of time, CPU time. You waste that CPU time. That's not a good thing. For that case, maybe if you know that you are not going to block, using spin locks is better. Okay, spin locks is better. So there is a new notion of fast user space mutex. It says that it uses best of both worlds. Okay, blocks only if necessary and switch to kernel space. Okay, otherwise you stay in the user space. So you don't call any operating system routines. You call your user space routines, and that user space routine, if it can handle the lock, it handles the lock. Otherwise, it switches to the kernel space. Okay, so this is the solution. Otherwise, when you are calling this one, when you are calling acquire a lock or block, okay, this is a library routine. If it immediately calls a kernel call, if it's a kernel call, direct kernel call, then that means that you are doing the context switch. You are switching to kernel space. and that's expensive. Okay. The solution is, why don't we try as much as possible in the user mode, user space, and if it doesn't work, then we will switch to the kernel space. Okay. So that's the solution. We looked at this last time, P threads and mutexes, and these are the sum of the functions. These are the sum of the functions of the mutexes: initializing a mutex, destroying a mutex, locking, unlocking, and try-locking. What was the difference between these two? It says right here: acquire a lock or block. That's a mutex lock. Okay, when you call this, you either acquire a lock or block. But when you call this one, you either acquire a lock or fail. Okay, so this locks or blocks, this locks or returns a fail. Returns a fail means that I couldn't get the lock and I will not block you. So you make your decision. You make your decision. So if you are implementing something in the user space, this is a very useful function to call. Okay, with the mutexes, sometimes, I mean, remember our semaphore example, this one. Why do we have two semaphores here? One is for the mutual exclusion, right? This one is for the mutual exclusion. This one is for the counting if the checking if the buffer is empty or not. Okay. Same thing again. Okay. So that's why we use two of them. Okay. So most of the time, with the mutexes, you need another way of checking if the buffers are available. For that, we have the condition variables. Okay. For that, we have condition variables. They are almost exclusively used with the mutexes. Okay. You create a condition variable. You destroy a condition variable. Wait and signal and broadcast are the other important condition variable functions. Let's look at an example actually. Producer-consumer problem here. I have the producer-consumer problem. Okay. I have this many iterations. Şu tarafa geç. Yoklama nerede? Ha, geldi mi yoklama? Ha tamam, bu tarafa oturabilirsiniz, yeni geldim. I have the maximum iteration of this many numbers. Okay, I'm going to do it in a loop. That's okay. Then I have the mutual exclusion variable mutex here, pthread library, and I have two condition variables like the NP and full semaphores. Okay, and I have my buffer, a single buffer. Okay, this is my producer. Let's look at the main function first. Okay, this is the main function. Okay, I have two threads. Okay, and I have the initialization for a mutex here, my mutex, and two condition variables are initialized, and I am creating two threads. Okay, then I wait for them to what does this do? They wait for the threads to finish their job, right? Okay, and after that I release the condition variables and I release the mutex. Okay, so this is the main function. As soon as I create these two threads, they will start running. Let's look at each of them one by one. Producer, okay, index from 1 to maximum. Okay, so this is the mutex lock and unlock. Okay, I get the lock. If I get the lock, I get it. If I don't get the lock, I block, right? This is the producer. And the second line after the locking is the condition variable. It says that if the buffer is available, condition P, this one. the producer condition, it's a condition variable for the producer. If the buffer is available, if I got the mutex, and otherwise I wouldn't be here, right? And that means that okay, there is a while loop. While loop says that if buffer is not zero, what does that mean? If buffer is not zero, that means that buffer is full. Okay, so I would ask the operating system to suspend myself until the condition variable for the producer is set with the mutex. So when I do this, if the buffer is not full, okay, if the buffer is not full, I would continue. If the buffer is full, if the value is not zero, then I would suspend with these conditions. Why do I need to send this mutex to this wait function? Why do I need to send this mutex to the wait function? Can anybody guess? Remember what we said? We said that condition variables are almost exclusively used with the mutexes. Okay? A condition variable without a mutex is not that meaningful. Mutex is a lock. Condition variable check to see if the buffer is available or not. Okay. So why do I need to send this value? Why? Remember the semaphores? Semaphore was doing the down mutex and down empty, right? It was doing two things. One was for the mutex, one for the buffer. So two statements, but the second statement here is doing this. Why do I do this? Because when I am waiting, okay, when I am waiting for the condition variable, when I am waiting to condition variable to be available, I need to release this mutex. Otherwise, nobody can get the lock, right? If I get the lock and if I sleep, okay, nobody will get the lock. This one, when the consumer starts running and the other thread is sleeping, okay, then it will not get this lock and both will sleep forever, okay? So the operating system knows that if somebody is waiting for this condition variable, okay, for this condition variable with this mutex, then it needs to release that mutex so that other people can use it. Okay. So if I pass this line, I say that buffer gets the value of I, so the producer produced the value, and then I did this feed-red condition signal. What does this do? It says that, okay, wake up the consumer because I produced something. Wake up the consumer, I produced something. Then I release the mutex. Okay. So when the loop is done, which is a very large loop, I kill my thread. Okay. Look at the consumer side. On the consumer side, I get the lock here, and I release the lock here. And again, if the buffer is zero, that means that no numbers in the buffer, nothing is available. Then I wait for this condition variable to be available. Okay, condition variable to be available. Condition C, with this mutex. If I am sleeping, then I need to release this lock. Otherwise, the whole thing hangs, and I wouldn't get anything. And when I consume the produced thing, all I do is this. So this is a very simple line. I mean, this is a toy example. Nothing useful is coming out from here, but it's a toy example. And when I am done, I signal the producer to produce something else. So when I am done, okay, when I say signal condition P, if somebody is waiting here, okay, condition P, if somebody is waiting here, it can continue. Then I release the lock. Okay, I release the lock. Any questions? Okay, so this is an example of producer-consumer problem implemented using mutexes and condition variables. Mutexes and condition variables. Wait and signal mechanism. Condition variable, wait and signal mechanism. You wait on some kind of a condition variable with the mutex, and if the condition variable becomes available, then you continue and you do the same thing. Similar to the semaphore example, we have two. Remember, in this semaphore example, we had two semaphores. We have three semaphores. One for the mutex, one for the down, one for the empty, one for the full. And in this one we have one mutex for the mutual exclusion lock, and two condition variables, one for the consumer, one for the producer. Producer signals the consumer when it is done. Consumer signals the producer when it is done. Okay. Consumer signals the producer when it is done. When it is going in, okay, it says that I am waiting for the consumer condition variable to be available. Okay, any questions? Can someone ask a question? Bir tane soru sorun.